When multiple wave pulses interact with one another or overlap one another, we call that interference. And that interference sets up one of two kinds of particular patterns. One kind is called constructive interference, and the opposite is called destructive interference. So we're just going to draw out a few simple examples of what situations could lead to both kinds. If we look first at constructive interference, we're going to just start with a simple example, but we need to remember that we're dealing with multiple wave pulses. So we need to have at least two different wave pulses that are going to interact with each other somehow. So we'll start with the case of someone that creates a wave pulse at one end of a string, but there is also another wave pulse coming at it that someone created at the other end of the string. And the idea is that this wave pulse that is on the left is heading from the left towards the right, and the one on the right is actually heading back towards the left. So maybe two partners, let's say, have each created a wave pulse at opposite ends of the string, and those wave pulses are traveling towards one another. And just for clarity, I'm going to call this wave pulse A, and this will be wave pulse B. Now eventually, if we wait a second or two longer, those are going to meet. And so in the row below, we can draw what would happen when they actually meet. And because each one individually has their own energy, and the amount of energy that each pulse has determines how large its wavelength is, when they overlap, the amounts of energy that each pulse had will add together. And so what we'll end up seeing is one larger amplitude that's really a combination of both of the original amplitudes. It should be twice what the original amplitude was. And so we see them meet right in the middle with one great big giant crest and then continue on. And so you can even draw in a little extra dotted line where the original size of the amplitudes would be, just so that you can recognize what's actually happening is that they've doubled. They've overlapped one another. And so really this giant crest that we have is A plus B. It's both of those pulses being added together. But we actually have a special name for this. Because it's not just a regular crest of a pulse anymore, it's much larger than that, we give it a name to represent that. So this is actually called a supercrest, meaning a crest that's formed as a combination of multiple crests. And that super word means bigger or larger than it was before. And so they're actually going to overlap and create one much larger overlapping crest called a supercrest. But then it's important to remember that after that, those wave pulses don't bounce off one another. They're actually traveling right through one another. So in the last or final stage here, I'm going to draw what looks like a very similar situation to what we had initially with pulse A and pulse B, but now they've switched. So pulse B is actually now on the left side, continuing to move farther to the left. And pulse A is now on the right side, continuing on farther down the line to the right. And so they've passed through one another. There was a split second where they overlapped, and now they've continued on in the same direction. That's constructive interference because we've constructed or built something that was much larger than the separate amplitudes that comprised it. Destructive interference still comes from the case when two pulses interact with one another, but it's when specifically two opposite kinds of pulses interact. For example, a crest interacting with a trough. So we're going to draw a very similar situation to what we did with constructive interference, but now it's going to be a crest and a trough that are moving towards one another. But once again, I'll call the crest pulse A, and I'll call the trough pulse B. Pulse B is moving towards pulse A, and pulse A is moving towards pulse B. So they're still moving towards one another, and they are eventually going to interact. If we wait just a little bit longer, though, if they're the same amplitude, I know mine aren't exactly the same amplitude the way I've drawn them, but if we imagine that they are the exact same amplitude, think about what would happen when they overlap. Well, all of the energy going above the rest position would be canceled out by all of the energy from the trough below the rest position. And so all of that energy trying to push the wave up is completely balanced by all the energy trying to pull that wave back down. And so what we actually see is a perfectly straight line all the way across. But we should still identify that it would only be for one split second at one particular location where that would occur. And so at one particular location, there'd be one spot that would represent right in the center of those pulses. And then what we're really seeing is that this is where we can imagine we have our upwards pulse and our downwards pulse, in other words, our crest and our trough, are overlapping one another, but canceling one another out. And so we get a completely flat line in one particular point along the string. And actually that one particular point, at the exact spot where we get that perfect cancellation, we give that a special name as well. It's called a node. So constructive interference produces a supercrest. Destructive interference produces a node. But again, remember that the wave pulses don't bounce off one another. They do continue on. And so a little bit later on, if we give it a split second longer, suddenly the trough will have continued farther to the right, or the left, I should say, and the crest will now be farther to the right. So now remember, this is still pulse B, which will continue to move down the line towards the left, and this is now pulse A, which is continuing to move down the line towards the right. So in general, when we say superposition, we really just mean it's an addition of the amplitudes. It's an adding or a sum of what the two energies actually are. And we can consider it a sum as long as we think of troughs as negative amplitudes and crests as positive amplitudes. That's why when we add equally sized crests to troughs, they cancel one another out completely and produce a node. We'll talk about this more in class and see some other examples more visually where you can actually observe this more in motion.